Good morning, my friends, and welcome to day 8 of our AP Calculus free response question Advent Calendar. Let's see if we can find the 8th little compartment on this Advent calendar, and then we can do some calculus. I'm thinking it is, let's see, there it is. I have no idea what's behind this, but I'm guessing it's not a bear. Let me zoom into this for you. Here on the side, it's right by that beautiful candle. Look at that. Really puts me in the Christmas spirit. Like you're walking through the village, you got windows dimly lit by the flicker of a tiny candle. Very nice. While I get into this square, I'll put today's free response question on screen so you can give it a read. Today's question concerns some cool stuff. We're going to have to do like a trapezoidal sum. That's going to be pretty fun. And it's another green ball, not a bear, just as predicted. I'm getting pretty good at just extracting these balls without having to, do any funny business. All right, let me have this chocolate, and then we will get into our calculus. We'll have to use our calculator a little bit today, I think. Whole lot of calories in all these chocolates. That's pretty good. I'm in the mood for a rectangle. I hope we get a rectangle tomorrow. But let's, for now, just worry about today's calculus problem. This is problem 3 from the 2005 AP Calc AB exam. It is part of the graphing calculator section. Let's read it. A metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature, T of x, in degrees Celsius, of the wire x centimeters from the heated end. So for example, 5 centimeters from the heated end, the wire has a temperature of 70 degrees Celsius. The function t is decreasing, which we see in the table, and it is twice differentiable, which means its derivative is differentiable, and thus its derivative is also continuous. Let's read part A. Estimate t prime of 7. Show the work that leads to your answer and indicate units of measure. So T, remember, is the temperature of the wire, x centimeters from the heated end. So T prime is going to be the rate of change of the temperature. And here we are asked to estimate it. Estimate T prime of 7. We can do that with a secant line, or more precisely, the slope of a secant line. In other words, we need to find the slope between these 2 points, because x equals 7 is between x equals 6 and x equals 8. So the best approximation we're going to be able to get with this data, the best approximation of the rate of change of t at x equals 7, will be the rate of change in this space near x equals 7, the rate of change from x equals 6 to x equals 8. To calculate that average rate of change over that interval from 6 to 8, we just need to take the change in the temperature and divide by the change in distance. So we have that t prime of 7 is approximately the average rate of change from x equals 6 to x equals 8, and that is 55 minus 62, that's the change in temperature, and divide by 8 minus 6, the change in distance. This is equal to -7/2. But remember, we also need to indicate units of measure. In this case, this is how the temperature, degrees Celsius, is changing as we travel more centimeters across the wire. So this is -7/2 degrees Celsius per centimeter. When x equals 7, the temperature of the wire is changing by about -7/2 degrees Celsius per centimeter. As we go forward another centimeter, we're dropping about -7/2 degrees. Moving on to part B. Write an integral expression in terms of T of x for the average temperature of the wire. For a continuous function like T of x, to find the average, we just need to add up all the values from 0 to 8, which we do with an integral, and then divide by the length of that interval, which is 8. Then we need to estimate the average temperature of the wire using a trapezoidal sum with the 4 subintervals indicated by the data in the table. So the interval from 0 to 1, from 1 to 5, 5 to 6, and 6 to 8. So we'll have 4 trapezoids for that. And again, we'll need to indicate units of measure. All right, let's start with the integral expression for the average temperature of the wire, and we'll do that down here. This is just a basic definition you should know. In order to find the average temperature of the wire, we need to integrate the temperature over the applicable interval, which is from 0 to 8, from the heated end to the other end. We need to add up all those temperatures, and then we have to divide that by the interval length. So we'll just put a 1 over 8 in front. That's dividing by 8. And that is an integral expression in terms of T of x for the average temperature of the wire. All right, now we're going to estimate this using a trapezoidal sum. So I've just copied the integral representing the average temperature of the wire, and this is approximately 1/8 times our approximation for this integral. We're going to approximate that integral using a trapezoidal sum. So let's come up to this data and recall the area of a trapezoid and how it applies in this situation. I'll just do a little sketch representing this situation. The first interval is from 0 to 1, so we can kind of sketch this base that has a length of 1. On the left, the trapezoid goes up to a height of 100, and on the right, it goes up to a height of 93. Since this function is just decreasing, let me make this highest value of 100 a little bit bigger. All right, and then this other side goes up to about 93. Okay, so we have a trapezoid that looks something like that. The next trapezoid goes from 1 to 5. I'll do that in a different color, say blue. So maybe we go from 1 to 5, and this thus would have a length of 4. Going from 1 to 5 means this base length is 4. On the left, again, it's going up to 93. And on the right, it's going up to 70. So maybe right there. It's not perfectly to scale, but it's a decent sketch. And we have that trapezoid. The next trapezoid goes from 5 to 6, and the right side goes up to 62. And so on. I'll sketch the rest of this. So that's just a rough sketch of our situation. Remember, each of these numbers on the bottom is representing the length of these intervals. In the context of trapezoids, these interval lengths are actually the heights of the trapezoids. The bases of the trapezoids are these vertical sides, 100 and 93, 93 and 70, 70 and 62. Those are the parallel sides of the trapezoids, and that, by definition, is the base of the trapezoid, or the two bases. To find the area of a trapezoid, we just need to take the average of the bases, b1 plus b2, take the average, so divide that by 2, and multiply that by the height. So we need to find the areas of all these trapezoids using that formula and add them all together. For example, the area of this red trapezoid is the average of the bases, so 100 plus 93, those parallel sides are the bases. Take the average, so divide it by 2, and then multiply by the height, which is the interval length, which is 1. This blue trapezoid we calculate the area of similarly. Average the bases, so 93 plus 70, divide by 2, because we're taking the average, and multiply by the height, which is 4, the interval length. And we can proceed with the rest of these areas in a similar manner. All right, there it is after writing all of the areas out. And there's another look at the sketch and the table, just so you can make sure you understand where everything is coming from here. Now, this here is our approximation for this integral using a trapezoidal sum. So when we multiply that by 1/8, we're going to get an approximation for the average temperature of the wire. And this turns out to be about 75.6888 degrees Celsius. And that completes part B. Let's move on to part C. Find the integral of t prime of x dx from 0 to 8 and indicate the units of measure. Then we need to explain the meaning of this in terms of the temperature of the wire. At a glance, we can say, well, this is the integral of the rates of change of the temperature. When we accumulate or integrate the rates of change of the temperature, we're going to get the total change from 0 to 8. But before we write that interpretation out, let's actually find this integral. The integral of t prime of x from 0 to 8 is very straightforward. If we integrate t prime, we are just going to get the original function t of x, and we're evaluating this from 0 to 8. So the value of the integral is t of 8 minus t of 0, and we can find those values by consulting the table. T of 8, we see, is 55, and t of 0 is 100. So the value of this integral is 55 minus 100, which is negative 45. We should specify this is degrees Celsius, so that is our value of the integral. And then here is our interpretation of what this means. This means that the temperature of the wire drops 45 degrees Celsius from the heated end at x equals 0 to the other end at x equals 8. That's because this is the accumulation of all the rates of change, so we get the total change. Let's move on to part D. Are the data in the table consistent with the assertion that the second derivative of t is positive for every x in the interval from 0 to 8? And of course, we should explain our answer. So for the second derivative to be positive means that this whole time, the first derivative, t prime, should be increasing. Now, we know the derivative t prime is negative. The temperature t is decreasing, so the derivative is negative. So for the derivative to be increasing, it should be getting less negative, which means that even though the temperature is decreasing, it should decrease by less and less as x goes on, and that should always be true. That's what it would mean for the second derivative to be positive. The first derivative is increasing. The first derivative happens to be negative, so it should be getting less negative, and the amount that our function is decreasing should be getting less extreme, because the first derivative is getting less negative. This is rather tricky, because we don't actually know any values of the second derivative, or any values of the first derivative. So how can we say that the second derivative is always positive, or that the first derivative is always increasing? Actually, we can use the mean value theorem to get a definitive answer to this question. Our function t is continuous and differentiable on this interval from 0 to 8. So the mean value theorem tells us that whatever the average rate of change is over some interval, that must be the same as the instantaneous rate of change at some point in that interval. If we look at the average rate of change from 1 to 5, the instantaneous rate of change must equal that average rate of change at some point in the interval. Using this, we'll be able to find 2 points that must exist where the derivative actually has decreased. And that's going to show that the second derivative can't always be positive. So let's check this out. What's the average rate of change from 0 to 1? Well, that would be 93 minus 100, which is negative 7, divided by 1 minus 0. So it would be negative 7. So the average rate of change from 0 to 1 is negative 7. Since that's the average rate of change, there must be some point from 0 to 1 where the actual derivative equals negative 7. Now let's look at this interval from 5 to 6. What's the average rate of change there? Well, let's write it down. T of 6 minus T of 5 divided by 6 minus 5, the average rate of change over this interval, is going to be 62 minus 70 divided by 1, the interval length. 62 minus 70 is negative 8, so this is just negative 8. So we can see the derivative has actually gone down. By the mean value theorem, there has to be some point in this interval from 5 to 6 where the derivative actually does equal that average rate of change, negative 8. So at some point, the derivative is negative 7, and at some other point in this interval, the derivative is negative 8. So at some point, it must decrease. which means it isn't always increasing, which means the second derivative isn't always positive. So no, the data in the table is not consistent with this assertion that the second derivative is always positive. And there is our reasoning written out. By the mean value theorem, there must be some point c1 from 0 to 1 such that the derivative at c1 is -7, and similarly a point c2 in the interval from 5 to 6 where the derivative is -8. And since our original function t is twice differentiable, we know that the first derivative must be continuous. Thus, it couldn't have just jumped from -7 to -8. It actually had to decrease somewhere, and so t double prime isn't positive for every x in that interval from 0 to 8. And that completes our solution to free response question 3 from the 2005 AP Calc AB exam. Let me know in the comments if you have any questions, and if you're enjoying the AP Calc free response question advent calendar, please consider joining Wrath of Math as a channel member to help me create more high-quality calculus content and to get access to exclusive calculus videos and other cool perks. Thanks for watching, and I'll see you tomorrow for the next episode of the Advent Calendar.